I will begin with a word of prayer. Heavenly Father, we thank you for this day. Pray you help us to use this time wisely. We'd accomplish much today, Lord. In your name I pray. Amen. All right, so first I will read you a list of long overdue quantum mechanics problems I should have assigned you ages ago at this point. Personally, I like the chapter 3 problems. I'm sure there's a good. I found a good one in chapter 2. Yeah. Okay, so let's do problem 2.36. Problem 2.37. Just to make sure we're on the same page with those, the 2.36 is a particle in an infinite square whale has the initial wave function sine cubed pi x over a. Find the expectation of x as a function of time. That's problem 2.36. Problem 2.37, you're asked to calculate the expectation values of position, momentum, the square of position, square of momentum, the kinetic energy. T is kinetic energy in this book. The potential for the nth stationary state of the harmonic oscillator. So we worked out those stationary states for the harmonic oscillator, so this is like sort of builds off that lecture to do a calculation. Okay. So that's 2.37. Then there may be some more in here, but I'm going to go ahead and here flip over to. Ooh, so interesting. No. Behave. No. I will not assign you that. Let's see here. Then how about number 35, 3.35? It's got A, B, C.
3.35?
3.35. It's on my page 108 in chapter 3. I'm wondering why problem 3. Well, let me not assign that one. Problem 3.37 might be helpful. And then problem 3.41, it's a good algebra exercise. Let's see here. Problem 3.50. This is a bracket battle. Problem tempted to assign 351. I'm not sure about that one. You can try 51 if it's too fuzzy, just skip it. 352, try that one. And 353 is an important result. That one would be nice to drive if you could. That's the viral theorem. Alright, let me see if there's anything else over here.
Is that named after somebody?
I don't guess so. I think 355 could be very interesting and maybe not that hard either. And then I think problem 3.57, if you understand that problem, that's a pretty good indication that you have a decent, at least introductory understanding of chapter 3 in here. So that's a kind of good capstone problem. It just looks like a mess of notation, but if you work through it, I think it's very instructive. Anyway, so that's that. All right, so you guys want to pick at the hyperbolic calculus some more?
Sure.
Let's try. So we found. Just remind myself what we did. We found that we found a solution to. Let's see here, phi UU minus phi VV equal to 0 that had 10 on this hyperbola, right, and 20 on that hyperbola. Using, what was it? Using 10 natural log of the square root of u squared minus v squared as it happens. I was thinking, you know, we have that's one solution, one kind of solution to the wave equation. We also have this as a solution to the wave equation. Let me think here. So in contrast, right, to the usual complex stuff, this is the complex one, right?
Yep.
So if you basically look at something like a natural log of the modulus of z plus b, this is a pretty good template solution for what? I mean, really, I usually put a w here, right? So we can fit you know, particular voltages to the inside and outside of an annulus or something, right? Boundary conditions, if you will. Now, the fact that it has to do with circles, I think we could also see from just setting this equal to a constant, right? Like, what happens if you set this component function equal to a constant? Think about it, right? We've got c equals to the natural log of the square root of u squared plus v squared, right? So you exponentiate both sides, square it, eventually you get u squared plus v squared equals to k, right? Here, if you set this equal to a constant, right? What happens is those level surfaces are hyperbolas, right? So when we look at a shifted, we multiply that by a and add a b. It allows us to adjust in different hyperbolas. We can pick up with level curves of that. This one, right? Both of these actually. Well, this, right? If you say that this is equal to a constant, what's that give you? That gives you that v over u equals to the tangent of c. In other words, v is equal to tangent c times u, right? So that allows me to find, I can find solutions to Laplace's equation which have a constant value along an angle. You know, so I can fit like a sector with this thing, right? I can make this 10, I can make this 20, right? And I can solve Laplace's equation on all that, you know, using a shifted one of these guys, I think. Like if I want to make that, you know, if this is, for example, if I want to make this theta equals to 0, make this theta equals to minus pi over 4 for our convenience, you know, basically I just do v equal to some a times, you know, a times u. Oh man, that's that. Well, how do I do it? I'm sorry, all of a sudden brain is broken. What's the solution to Laplace's equation for this? If I want this to be 10, and I want that to be, say, 20. And I guess the question is, where am I? I am in UV space, or am I in XY space? I mean, we gotta pick something, right? Suppose we're in, you know, what do you guys want to do, XY or UV?
UV.
UV, okay, so.
Well, when we just kind of plug it in and solve it for like we did before with like the A and B values.
Mm-hmm. Well, what do I do? I mean, is it? I guess it's just. I guess we just do like beta, perhaps. So phi equals to something like A beta plus big B. So I want when beta equals to 0. We want phi equal to 10. So 10 is B. And when beta is equal to, maybe I should make that not minus pi over 4. If I make it minus pi over 4, we're going to end up solving it in the byte rather than in the Pac-Man. So we should make that maybe, you know, what is it? 7? Yeah, thank you, 7 pi over 4. So beta 7 pi over 4. I got 20, right, is equal to A times 7 pi over 4 plus 10. So we can solve that. And that will give us what? Subtract 10, that gives me 10 is equal to 7a pi over 4, so 40 over 7 pi, is it? Is that right? So my phi
Yeah,
is,
you're right.
is equal to 40 over 7 pi beta plus 10. Now here, of course, to be more explicit, that's 40 over 7 pi, the argument of, you know, u plus iv, right, plus 10. Although it's not the argument, because I'm going from 0 to 7 pi over 4. So if we use 0 for the starting point of the argument, then I might say argo. Like, you could use arg sub alpha as the argument which goes from alpha to alpha plus 2 pi, not included.
That has to do with like you're talking about the like initial.
Yeah, actually that's
Initial
kind of
alpha.
backwards of the usual argument too, because I'm including the lower bound and not the upper bound. The standard argument includes the upper bound, pi, but not the lower bound minus pi. So this is backwards of the usual inclusion of the, including 0 rather than 2 pi just because it's natural. And anyway, it's just a choice of angle, basically. It's the angle function. But anyway, that I'm trying to get at is that's coming from the level curve of that, right? So, but I was thinking about for a while, and I didn't really get much anywhere on it. I'm still somewhere off, and I'm not sure where I'm at conceptually. I'm floating. This being a constant is well, what's that? I mean, if I set inverse tangent of v over u equal to a constant, what's that look like? What do we get then? It's kind of interesting, right? We get v over u equals to the hyperbolic tangent of c.
Which is again a constant.
Right, again a constant, so in other words we get v equals to hyperbolic tangent of some constant times u. So those are sort of the, I mean that's another solution to the wave equation, the phi uu minus phi vv. I mean it's pretty obvious that that solves that, right? second derivative is 0, but. Sorry. Wrong thinking. This is the thing that solves it. It's not at all obvious that that solves that, but it does.
Right.
Right, like derivatives of the inverse hyperbolic tangent, it's like 1 over 1 minus v over u quantity squared times the derivative of the chain rule, and then you differentiate again. There's a couple of quite awful quotient rules here, but things cancel and it ends up being 0.
Never use the quotient rule.
It's also never use it.
Bad. Always product rule.
It's also, by the way, not entirely obvious. I mean, this is a solution to Laplace's equation for similarly complicated reasons. If you take 2 derivatives in u and 2 derivatives in v and you add them, they cancel out to be 0. Because of the different way v and a u appear there, one reciprocally and one not. Now, here's the difference. Tangent, right? Now, if you look at the level curves of this function, right? Level curves of this function are lines through the origin. And the tangent of c can take any value. The range of tangent goes from minus infinity to infinity. All slopes are possible. Hyperbolic tangent, in contrast, level curves of this are lines, right, through the origin again, but only allowed hyperbolic tangent. Remember, last time I showed you guys, hyperbolic tangent is stuck between minus 1 and 1, not inclusive. So these level curves of this, they're stuck between these, there's these, this is v equals u and v equals minus u. These are not even attained. I mean, this would take tangent of minus infinity. This would take tangent of infinity to get to those. These are enveloping. And of course, the hyperbola solutions asymptotically approach these guys if I drew it better. But as you vary c from minus 1, I mean, as you vary c from minus infinity to infinity, the hyperbolic tangent goes from minus 1 slope up to 1 slope. And you've got everything in between as well. These are these kind of level curves. So I guess if I wanted to solve, I guess if I wanted to solve the wave equation in a sector, right, like, I could try to solve the wave equation in here, I could look at something like, I guess I would look at something like phi equals to a times, oh man, I also use gamma. Is that the right thing to use? Actually, we usually use, ironically enough, we usually use phi. But that's bad, I can't use that. It seems to me this is the rapidity, but 7. I'll just use alpha, a alpha plus b, where alpha is equal to the inverse hyperbolic tangent of, v over u. I ought to be able to fit that to, if I want. Let's see here, let's try out something explicit. So suppose I want to solve a wave equation in here. So here is v equals to u over 2, and here is just, v equal to 0. Suppose I want to solve in here, and I want to put 10 here, I want to put 20 here. I think we can do that with the template phi equal to A alpha plus B, right? But you got to be careful. I mean, you're used to angles, right? So when I told you that that was 0 degrees and that was 7 pi over 4, you know what I was talking about, right?
Mm-hmm.
So we've got a bit of a learning curve here. We have to figure out what hyperbolic angles, how do hyperbolic angles work, you know? So what I was arguing was that basically I'm saying that this is c equals to 0, and this up here is c equals to infinity, and down here you've got c equals to minus infinity. These are the so-called hyperbolic angles.
So is that saying that the line v equals e over 2, that's going to be their just infinity in this case? We're kind of adjusting it, or are we?
I don't know what that's going to be yet. We want 1/2 equal to the hyperbolic tangent, right?
Yeah.
Of whatever the angle is we're looking for. So this is going to be c equal to inverse hyperbolic tangent of 1/2, whatever that is.
Oh, I do actually have a calculator for that.
You calculate or have inverse hyperbolic tangent on it?
Yes, it does.
Holy cow.
Nice.
Yep. 1/2.
See, like I thought he was punching something into his phone. He's got a Wolfram Alpha app.
No.
The TI-36 Pro does it?
Yeah.
Oh my gosh. So 0.55 roughly speaking.
Yeah.
Cool.
It also does complex algebra on it. Well, adding and
Oh,
subtracting,
neat.
dividing.
Neat.
whatever.
So let's see here. So anyway, what we have then, right, is 10 is equal to a times 0 plus b. So therefore b is equal to 10. And 20 is equal to a times, roughly speaking, 0.55 plus 10, right? So therefore a is equal to 10 divided by technically the inverse hyperbolic tangent of 1/2, right? And so the solution then that satisfies these boundary conditions is phi equal to, phi of u plus jv in the hyperbolic numbers, right, is 10 over the inverse hyperbolic tangent, which we could find a decimal of, but whatever. Thank you for that. Inverse, I mean, it's kind of funny. It's like close to 1/2, but it's not. It's anyway, inverse hyperbolic 10 divided by inverse hyperbolic tangent of 1/2, and then alpha. What is alpha? Well, alpha is inverse hyperbolic tangent of v over u, and then plus 10. That is a function that solves this equation, right? And you can kind of see here, if you put, you can see it, right? If you put v equals to u over 2, you get inverse hyperbolic tangent of 1/2 upstairs and downstairs that cancel. You get 10 plus 10 is 20. And the inverse hyperbolic tangent of 0, well, that's 0, so you get 10. So you see we've solved that. We solved that that problem there in that sector. So we can solve the wave equation for sectors between the lines v equals plus or minus u. And we can also solve the wave equation between between hyperbolas using the log of the difference of u squared and v squared square rooted.
Question.
Yeah.
So like the part of that formula down there, phi of u plus jv equals all that. There's not really any angular part of that. Like we're not plugging in a hyperbolic angle.
Well, that's the thing. Inverse hyperbolic tangent of v over u is a hyperbolic angle.
Yeah. So shouldn't that angle we were discussing before, shouldn't that be equal to like infinity or something? Kind of like over there, you said like a chunk would be from like 0 to infinity. Well, you said like the axis, the u-axis, is c equal to 0, and the other one up there, like v equals u, is going to be c equals to infinity.
Right.
Why is that not the case in this part, even though it's kind of similar?
Well, if I put v equals to u, I get infinity there. If I let v tend to u, then I get inverse hyperbolic tangent of 1, which is infinity. So this solution will blow up on the asymptotes.
Okay.
It blows up to plus or minus infinity, depending on if you're going to the upper asymptote or the lower asymptote. But it does blow up. It also happens to match 10 and 20 as we want in the sector of interest.
Okay.
It's kind of funny, right? Like, it seemed to me, well, I'm trying to remember. You know, it's also true for the log solution, like I have at the top on the donut, that while we engineer the thing to match a given voltage at one inner and outer radius for an annulus, the solution extends past the annulus, right? It only blows up when you go to like w equal to 0.
Yeah.
So I guess this isn't a new phenomena to the hyperbolic, that, you know, our solution, it fits a particular pair of boundary conditions, but it still makes sense past those.
Yeah.
There are other problems where you fit boundary conditions to the edge, and that's just the edge. I mean, there's nothing, the formula doesn't make sense past the edge. But this is not that.
So you're saying like this kind of problems could like relate to like problems such as like things that have to do with like charge densities?
Oh, I don't
Like-
know. I don't know what this means. The hyperbolic stuff?
It kind
I
of
have
seems
no
like
idea.
it from the way you're talking about. Like it,
Well-
like almost like you can measure stuff emanating from like. The,
I mean, let's see here if I can hazard a physical interpretation.
I mean, you don't have to. I think I'm not trying to start.
Well, I'm nervous to try this, but
you don't have to if you don't want to.
it's okay. So, okay, like going, you know, from here, past this point in our study, so now we at least, we have ownership of the solution to a sector. So if we can find hyperbolic functions that map to that sector from the xy plane, you know, the z equals x plus jy points, then we can take these and we can transport them back and find weird solutions to the wave equation in the xy coordinates. That was our sort of penultimate goal. Actually, it's not my ultimate goal, but it's
a step.
it's a cute example, really. Okay, so you guys know space-time. I don't know, maybe you do, maybe you don't. So in space-time, we have x naught equal to ct, and we have, well, usually x1, x2, x up to 0, x upper 1 is x. And so the let's see here, how's it go? And then so you have the x sub mu, x upper mu, depending on the conventions. Let's say it's minus c squared t squared plus x squared plus y squared plus z squared in R4. with a typical thing being, CT, X, Y, Z. This is the invariant interval. If you change coordinate systems to another inertial frame of reference, this is invariant. So if we let's just focus on space-time.
Do you want the t squared, or is that supposed to be?
Yeah, it's supposed to be t squared, thank you. So if we look at, let's see here, ct prime, x prime, well, that's going to be equal to something like this. Gamma minus gamma beta, minus gamma beta, gamma ctx. So that gives you gamma times ct minus beta x, and gamma times x minus beta ct.
Isn't that formula up there, the x of mu, x upper mu? Isn't that just like the dot product we just kind of talked about before in advanced calc? Like that formula, like negative c squared, t squared plus x squared, yada yada yada.
I forget what I talked about in advanced calc.
I think it was brought up in
hurts.
Renelin.
Ouch! Ay, ay, ay. What's wrong with me? Yeah, I may have talked about it. It's the invariant interval.
Yeah.
It's the Minkowski metric.
That's
You
it.
know,
Yeah.
I mean, this is working towards describing the hyperbolic geometry of Minkowski space. That's what I'm working on. So these are Lorentz transformations, If I divide through by c, we've got t prime equals gamma times t, and the beta is the speed over the speed of light. So here we're talking about two frames of reference that are coincident at time 0, and this one's moving with velocity v relative to the other one. So beta is the ratio of the velocity at which the origin of the prime system is moving in the unprimed system. And so t prime is equal to gamma times t minus, so that's actually vx over c squared. Here's the formulas you tend to see in the introductory physics book if you read that part of it. And x prime is gamma times, x minus, and here the c's cancel and you're just left with x minus vt, right? And the gamma is 1 over the square root of 1 minus beta squared, which is, by the way, 1 over the square root of 1 minus v squared over c squared. What am I trying to get at here? So you can define something called rapidity, all right? The rapidity is, how do we define it? It is defined by hyperbolic tangent. It's the hyperbolic tangent of the rapidity, which we usually use phi for in physics, is equal to beta. Now, tanh is equal to sinh over cosh. So that's equal to beta, right? So sinh squared phi is equal to beta squared cosh squared phi. But remember, cosh squared can be written in terms of sinh squared how? Cosh squared minus sinh squared is 1. So if I want to rewrite cosh squared in terms of sinh squared, I get what? 1, again, cosh squared phi minus sinh squared phi is 1. Goodness gracious, these markers are all trash. So this is, what is that? That's cosh squared is 1 plus sinh squared, right? Right? So here we got this identity between beta squared and sinh. what does that force cinch to be in terms of beta? Can you see it? We've got cinch squared. Hey, marker, that works. Cinch squared phi times 1 minus beta squared equals to beta squared. Subtracting that to the other side, you know? So cinch squared phi is equal to beta squared over 1 minus beta squared. Which is, by the way, beta squared gamma squared. See this gamma? It's the standard fudge factor of special relativity. Basically, take anything in classical physics, you stick a gamma on it, voila, special relativity. And it's a little bit sloppy, but it's not too far from the truth. Anyway, so yeah, cinch, the hyperbolic cinch, hyperbolic sine of the rapidity is equal to beta times gamma. And the hyperbolic cosh of the rapidity is just equal to gamma. Right? Because the quotient of these has to be beta, that forces cosh to be gamma. So after this little exercise here of hyperbolic mathematics, we have found our way to what? So if you look back here, right, we have that CT prime, X prime is actually equal to cosh phi minus sinh phi. And man, was there moment of doubt. I'm not sure about that minus on the, I'm not 100% sure about the well, fine, I'll just stick with my first memory is usually right. I just doubt it now about this minus. Anyway, that's somewhat unimportant to what we're talking about. Not entirely though. So my point is, the coordinate transformations in special relativity involves transformations by hyperbolic angle. Rapidity is the hyperbolic angle. So you see, when you look at something like x squared minus c squared t squared equal to some particular constant, you know, this is the invariant interval, right? If two events are the same event, I mean, how can I say this? If an event, right, is measured in two different inertial frames of reference, it has to have the same invariant interval. So in other words, if you have an event, you know, which is at x, which is at ct, comma x, if the event is at ctx according to s, via the observer s, then if the same event is at ct prime x prime via an inertially related observer s prime, then you have to have that x squared minus ct squared is equal to x prime squared minus c squared t prime squared. So in this sense, different inertial observers have to agree on events. They can have different time and different position, but this particular quadratic combination of position and time has to be agreed upon for an event. So I don't know, like fuzzy relation, but you know, it's hyperbolic angles over here. So if I think of, you know, I don't know which one would be space and which one would be time. You know, I need to make a little bit of readjustment here. I mean, so we have, it's weird, this is weirder than it needs to be because we're thinking about the conformal mapping idea on top of things. So let's track it back here a little bit. Let's go back to X and Y, just for the sake of, maybe that doesn't help actually. Maybe I'm gonna stick with U and V. I might stick with U. So, you know, we have, I take it back, I'm gonna stick with the U and V. So we have phi UU minus phi VV equal to 0, right? What I was showing you guys yesterday, that has to arise from the algebra equation. What algebra equation does it arise from? This is basically interchangeable with the algebra equation 1 times 1 minus j times j, right, equal to 0. The reason I have the wave equation over the hyperbolic numbers is because I have this equation over the hyperbolic numbers. And if I want instead, suppose I want instead this equation, phi xx minus c squared phi tt. Do I want that though? See, I feel like I don't want that. I feel like I would want this, right? Oh, V's bad. I use C for the, I'm thinking, if I was looking for that, I don't know what I'm doing, guys. Sorry. But let me just one step further and then I'll stop talking about this. I don't know where I'm going. I'm just playing. If I had this, that would have come from what? From an algebra where you have something like c squared times 1 times 1, right? Minus, say, k times k equals to 0. So we want something like k squared equals to c squared, which would not be the hyperbolic numbers, it would be like a modified hyperbolic numbers.
So it'd be like a CJ.
Let's see here, so I want to show you guys this stuff anyway. It's kind of independent of other things we're doing in some regard. I mean, it's just kind of a bit of physics. I may have showed you that before, I forget. I don't know.
Physics 1.
Physics 1. It's possible.
I mean, not that in depth, but you know, relatively.
Yeah. So if we look at this algebra, right? R plus KR with k squared equals to c squared, where this c is a fixed positive number, right? C, a fixed positive number. So we usually have it equal to 1 for hyperbolic numbers, right? Then you could work out, like, you know, what are, what do, first of all, what's the isomorphism to the direct product of R and R with this? Sorry, it's kind of a weird way to go. So this is A is isomorphic to B, which I called R cross R last time we talked. You know? So check it out. We have in A K over C squared is equal to 1, right? So K over C is like my quote-unquote J. I want to map that to 1 minus 1 like we did yesterday. And so my isomorphism would be this. A plus BK equals to, oh, sorry, I'm getting ahead of myself. Where am I? I am. So A of K, goodness gracious. Words. Psi of K over C should be equal to what? Should be equal to 1 minus 1, right? Psi of 1 should be equal to 1, 1. My goal right now, guys, is to show you how we can produce particular well-known solutions to the wave equation using the A calculus. I saw this in Waterhouse, which is a paper by a pretty good mathematician. I think he's dead.
Was the particular?
They're all dead. Anyway, sorry. Like I found obituaries for most of the people I mentioned yesterday from the 90s to a month ago. All right, so the formula for this is what? If I want a linear transformation, which, so this says that psi of k, right, is equal to cc, minus c rather. So the matrix of psi is 1, 1, c minus c. And so from that I can tell you the formula. A, psi of A plus bk should be equal to A plus cb, comma, A minus cb. As a check on my isomorphism, notice that if we plug in, what's the deal with psi of k? Psi of k is what? It's c minus c, right? And so if you look at psi of k squared, you get c squared, you get c squared times 1, 1, which of course is c squared times psi of 1. Which makes sense because k squared is equal to c squared, right? So it's a good check. All right? This is the isomorphism. What's the inverse?
Just inverse to 2 by 2.
Right. Yeah. Actually, we'll get to that when we get to it. How about that? Now, if you have a function, right? Let's say f1, f2, mapping on the direct product of R with itself, what does it look like? What does a B-differentiable function look like? So let's see here how to get to this. So the matrix of this, it looks like the following. It looks no, goodness gracious, not that, but it's things like this. It's C1, C2, 0, 0, such that C1 and C2 are in the reals. That's what the matrix representation of the direct product algebra looks like. We can work it out, like, if you want. So if I want A comma B times X comma Y to equal to some matrix times XY, right? Well, this is equal to what? I mean, I'll write it up here. This is AX. This is BY, right? So to make that happen, you have to put A here and B here and zeros all the way or else. The matrix representation of a direct product is really stupid. But that's really interesting, and that's part of the reason I was trying to get you guys to think about that, is it makes the analysis, in some sense, stupidly trivial. Because what this means, right, this is, so if f is an element of the B differentiable functions, right, what that means is that the Jacobian matrix of f, which by the way is what? It's partial x f1, partial x f2, partial y f1, partial y f2, if you'll allow me that language. That's the Jacobian matrix with these component functions. All right, and that's an element of what? That's an element of the regular representation of the B algebra in my lingo. And so what does that mean? That means that the partial derivatives, which partial derivatives are zero?
We just said an equal, don't we? And the no.
I think you do hard. You have this matrix is the form of a generic matrix in the regular representation of the B algebra. This is a Jacobian matrix. It's in there. What does that say about the partial derivatives?
So partial y f1 is 0 and partial x f2 is 0.
Exactly. So this is 0, and this one's 0. So there's no integration or anything here. It's just that what that means is that f1 is equal to f1 of just x. And how about f2? Well, f2 is equal to f2 of y. They're just functions of x and y respective. Completely arbitrary though. That's it. Just that's the condition. It's just a function of x. Just a function of y. Real differentiable, I suppose. Okay, so now you have to ask yourself the question, if that's what a typical, so we have now described a typical B differentiable function. It's a pair of functions of just the first variable and just the second variable, right? So in other words, we've just found your archetypical B differentiable function. It's f1, f2, where, so f of xy is equal to f1 of x. Why am I working around that? I'm erasing that. It's equal to f1 of x, f2 of y. All right, that's your typical function over the B differentiable function. So what does a typical A differentiable function look like then? We use that theorem to, I can take this B differentiable function and I can pull it back through the isomorphism. Let me draw a picture to remind myself how to do it. So I'm trying to create a typical function here, right? Let me call it G. I've got a typical function down here, which I've called F. I've got this mapping psi, right? That goes from where to where? From
Our algebra into the B.
right, yeah. Psi goes Psi goes from A to B. It's supposed to be a B. So, okay. I'm debating whether I should draw it here or here to be productive. See, I want to define G by pulling it down through this typical F. So I'm just taking G to be any A differentiable function, okay? So I can track, instead of going directly from here to here, I can instead go from there, and then I need my psi inverse. So In other words, I'm claiming I have an identity that is, I can rewrite G as, you know, like this. So psi inverse composed with F composed with psi. I can do that for any G. I have this identity that allows that's given to me from this isomorphism. What's that mean? I guess we need the psi inverse. Can you tell me what it is, Jess?
Psi inverse of like the actual function or what?
Yeah, what's psi inverse of say x, y? Wait a minute, psi
matrix
inverse.
is just
Let me decide here.
the matrix.
Psi inverse of x, y. Oh, I just do them.
Matrix is just going to be minus C, minus 1, 1. Right?
So 1 over minus 2c,
Yeah, divided by determinant.
and then I got a
Flip them.
minus c, a little bit more exciting this time, and then minus c minus 1.
Yeah.
Let's see here.
Equal to x over 2 plus y over 2. Yeah.
X plus
1 half
y?
x plus y, yeah.
1 half x plus y. Comma. Cx minus cy, right?
Wait. I think it's over. I think it's over C. Isn't it?
Over c? Oh.
Yeah.
So x minus y over c.
Yeah, that's it.
So, no, but what this really is x plus y over 2 plus k over 2c times x minus y. Right, because we're our psi inverse goes from the direct product algebra, right, back to the algebra which has k and 1 as its basis. Yeah. Okay, so great. Let's put that into practice. Then we want G of what? We're looking at G. I should use something other. Unfortunately, I've used x and y for coordinates on B, so I should probably use something else for coordinates on A. I don't know what you want me. I guess I'll use U and V for lack of a better idea. So G of U plus KV, right, is going to be, this is our identity, psi inverse of F of psi of that. What is psi of U plus KV? U plus C times B, which in this case is V, right? I guess I could use, why don't I just use A and B? I used that before. I'm an idiot. Let me use A and B. I was using A and B before, why don't I keep doing that? You know? There's no need to make it confusing. So this is A plus CB, A minus CB, no need to reinvent the wheel, all right? All right, now here's the thing. Now we use our calculation on the direct product algebra to simplify things. See, we use the observation that it has to run through the direct product algebra by the isomorphism. That says that this isn't just any old thing. This is F1, right? Which is just a function of what? A plus CB.